So I had like only one email until like 5 minutes ago and said like about a dozen. So we're going to start out with them in chronological order. First question I got asked was about a homework problem involving mass spec. Now it was more a question about how to draw the molecules it's looking for, but I do like how the problem actually starts out. So we're going to start with that question first. So the question is regarding something like this. So we have two compounds, one bromo, four propylbenzene, and preface this is Orgo 1, and three bromopropylbenzene. The question is, which of these two compounds correspond to which spectra? So I've got two spectra drawn, and it's asking me which is which. So to answer this type of question, because these compounds have the same atomic weight, how do you distinguish which ones is which? And I do appreciate your book actually covers this in edition 11. Edition 9 and earlier really doesn't go through it very well. Is in mass spec, not only do we see the weight of the parent ion, we also see the fragments associated with the molecule. So if you have, this is why we end up getting unique mass spectra for each compound, with the exception of stereoisomers. That gets a little bit more debatable. But in terms of constitutional isomers, yes, we get very unique spectra because we form different fragments. So the easiest way to answer this question is look for an obvious fragment. So let's split the compound here, and let's look at these two fragments. In this case, we've got a benzene ring, but it's missing a hydrogen, and it's a +1 charge. So we've got C6H5 plus, and in this case, we've got C6H4 Br plus. Now these have different atomic weights, but these would both be fragments associated with this compound. So the weight of this one, let's see here, 72 plus 5 should give me 77 AMUs. And for bromine, subtract off 1, give us 76. Sorry, 76 plus 79, 14155. 155, 156. And I'm going to do both because bromine actually has two pretty common isotopes. So if we see a fragment at 155, 156, we know that's a brominated benzene ring. So that is most likely what that compound is. So if I go to this one, I see a compound. I'm going to go with, I probably added it up wrong, 169. Let's see if I'm right. They're both correct. So this high peak here, this 169, well, actually there's your 156 right there. This comes about from a brominated benzene ring. Sorry, it would probably help if I actually showed you what I was talking about. So this peak here at 156 is associated with a brominated benzene ring. We don't have that in this top spectra. So this top spectra here has to be the 3-bromopropylbenzene. The bottom one has to be the 3-bromopropylbenzene. Now, drawing the structure for the ion that corresponds to the peak, base peak for the top spectrum. So I'm going to go with base here is probably the parent ion. Let's see if I can do that. So the 91. What would weigh 91? It's going to have the benzene ring in it, which is 77. So we need an additional 14 AMUs. So if I was to draw the 91 ion, it's going to be my benzene ring plus a methyl and a positive on most likely that carbon, if not the ring. Huh. Wonder what the answer is. I don't know what it means. Hepta-O. Sorry, it forms a ring. So to draw this molecule, it is a ring. Specifically, it is a 7-member ring. This has got to be painful to watch on the live stream. Forgot it will do a shift in order to stabilize that carbocation. So what you end up forming with this 91 peak is actually a 7-membered carbon ring with one of them being a carbocation. Now, the Orgo 2 students should know that this is a conjugated aromatic system, so that basically that's why it wants to do this. Is there a clean structure tool at all? So that's your solution here, is that you end up drawing a 7-membered ring with a carbocation in the ring. Now, for the bottom spectrum, our base peak of 169. So let's see here. Well, we still got the 77. We need to add 80 is the most common peak for the bromine. So that's 157. And then 169, there's an additional 4. Or additional 12, so that's an additional carbon there. So it's probably going to be the same ring, but in this case with a bromine on it. So if I draw my 7-membered ring, where are you? I saw you. There we go. Sorry. Again, I know this is painful to watch. It's painful for me to draw. We've got our 7-member ring. We've got our methyl group that drops in there, but we have a bromine, and we need to keep track of where the bromine is relative to this carbocation. So this carbocation is formed at this carbon that is 1, 2, 3 carbons away from this methyl group, the CH2 group that's going to drop into it. So if we have our positive charge here, the bromine is going to be 1, 2, 3 carbons away from it. So 1, 2, 3 carbons away from it. And drop in our bromine. Oh, come on. Anyway, that is the answer. So as far as the question I got asked about how you draw these structures, to input the charges, you use the plus feature that's in there. The challenge with this one is actually getting the plus charge in the correct place. Be sure the heptarenal cation is drawn correctly. Thank you. I know what happened. For those of you who are curious, there is no good drawing software for Homeworks. So that's the first email I got, was concerning how to draw the structures in this program. Second question I've been asked, also an Organic 1 chemistry question. Can you go over questions 15 and 65? So let's see what those are. I actually gave credit for question 15. I don't agree with what this is listing as the answer. So for those of you looking at question 15, organic 1, you've actually been given credit for this problem. I would say that for, I guess I can bring up the figure for you. In structure A, nitrogen is sp3 hybridized. It's got 4 things around it, including lone pairs. In structure B, it's sp2 hybridized. The carbon in both is sp2 hybridized. Your book does not agree with this. It says that, so definitely carbon is sp2 hybridized in both A and B. For, I think it claims that it's sp2 hybridized in both A and B. Yeah, that's what it's claiming. I don't agree with it. The lone pair there should put you as an sp3 hybridized carbon. So I'm not sure why the book is saying this, but I've got a lot of other references that agree with me and not the book. So we're going to go with my answer on this one. Go away. The other one, can you go over question 65? But yeah, just so you know, I got rid of question 15 if you're in Orgo 1. Oh, sorry, question 65. So a compound of molecular form of CH9NO2 had peaks for its benzene ring carbons at 113.8, 119.3, 131.6, and 151.4. Know the peaks for benzene rings carbons were present. Which compound is most consistent with the carbon-13 NMR? So to approach this, there are 4 carbons in the benzene ring, or 6 carbons in the benzene ring, and you've only got 4 peaks, which means that you're going to have some that are going to have to look exactly the same. So this is not too bad by process of elimination. So let me flip it back to the board. So if we've only got 4 peaks, it means that we've got at least 2 pairs that look exactly the same. So the only way to get this feature where you only have 4 peaks is that when we draw the molecule, we need a symmetry plane running through 2 of the carbons. So this is peak 1, or this will be a peak. This will be a peak, but because these are mirror images, this will be peak 3 and peak 4. Now, not necessarily in that order in terms of chemical shift, but this type of symmetry is the only way that we would get 4 peaks in the NMR. If we had a symmetry that was running between bonds, meaning something like this, we would only get 3 peaks. So symmetry is going to cut down on the number of unique chemical shifts you get. So let's use that as a first pass approximation. So if we go back to the homework problem and we look at it, this definitely has a symmetry plane running through the benzene ring, so this is a possibility. For this one, we don't really see a symmetry, we really don't see a plane of symmetry associated with it. So B in my case is not a possibility. We also have the possibility here with this compound, because we see the symmetry plane running through the benzene ring along the along the one that's bound to the NH2 and the carboxylic acid. And then we have this one where we got the carboxylic acid next to the NH2. Again, this isn't a possibility. So A and B are our 2 remaining possibilities. So now we had to start looking at the chemical shifts. So we have 113, 119.3, 131.6, and 151.4. So to get these chemical shifts, if we look at the ranges, well, basically we have 2 really down-shielded carbons, 131 and 151.4 versus 2 that are relatively more shielded, 113 and 119. So the question is, what will shield or de-shield these electrons? Well, something like a nitrogen here is going to be a shielding group. So we would expect to see in this compound on the bottom right, anything that's adjacent to this carboxylic acid is going to be shifted towards higher ppm. So that would account for one of our really downfield carbons. The NH2 here is actually going to shield. So we'd actually expect to see 3 peaks that are kind of close together in terms of shielding. Being adjacent to this oxygen is going to deshield it. So to figure out which of the functionalities is probably present, because again, A and D in this case are both possibilities because we have that plane of symmetry running between the 2 carbons. We would have to look at the chemical shifts, and because we have 2 that are fairly deshielded, my guess here is going to be that this is the compound. So let's check it. Molecule is symmetric. Apparently I was wrong. I don't know why it's claiming that one, but 50-50 shot, right? But the symmetry alone is going to be what kind of gets you there, and then it's just trying to figure out which groups end up shielding and de-shielding. Honestly, I probably should have just gone to a table and figured out which way these shifts go, but hopefully that helps you out. All right. 2 more questions. Where are we? Quick question that I got in the live chat. Where were we supposed to put the chemical reaction of separating mixture in the lab report? Either in the, so you got a few possibilities. It does need to be in there. It can be in your methods. It can be, methods or results would be the best place. If you want to put it in your data observations, that's fine, because that was technically what you were observing was that reaction. But it does need to, for those of you in Organic 1, you do need to have the reactions showing how you drove the different compounds to the different phases. All right, this is actually an Organic 2 question. So the first question. The acidity of hydrogens and basicity of organic compounds. And the context of the question is, the weaker the conjugate base, the more strongly held the unshared electron pair. So how do you apply this to compounds? So your CH bonds are, so the bigger question is, if you want to know if something is a good base, the question is, in this case, we're going to work with Bronsted bases. Even though we're technically working with Lewis acid base theory, this is going to be the easier theory to deal with. So if you want to know if something is, sorry, I'll read the question one more time to make sure I'm answering it correctly. So in terms of basicity, you can look at it in terms of the stability of the acid that's made. So if you want to know if something's a good base, see what it looks like when it becomes an acid. So to become an acid, we're going to look at we're going to add a hydrogen, so we're going to do the Bronsted theory. So if we add a hydrogen to this molecule, hydrogen to this molecule, and a hydrogen to this molecule, the better acid is going to produce the worst base. So the reason why your carbanion is such a great base is that this is awful at getting rid of its hydrogens. So if you look at CH3, the CH bond is incredibly hard to break. So if you ever form a carbanion, if there is any hydrogen present, it is going to abstract the hydrogen in a heartbeat. Now, if we look at phenol, alcohols actually do engage in this type of behavior. So they're actually quite good at losing their hydrogens. They're just not as good as something like a weak acid. So something like phenol would rather absorb a hydrogen. But the other thing is that because we get this resonance stabilization, this ends up being a little bit more stabilized. So this is more acidic, relatively speaking, than the CH3 group. Now, what makes this the most acidic is that when we do form this ion here, we actually have two ways to resonance stabilize. We can resonance stabilize with the lone pair that we form with by extracting the hydrogen, or we can do it with the existing lone pair that's already on the nitrogen. So this actually has two different resonance forms, which makes this better at being an acid than, say, something like the OH group, which doesn't. I know that's not really answering your question. So the actual question, which of the following labeled atoms is more acidic? Oh, actually I didn't need to answer that question to answer this one. Sorry. So the question that's being asked is actually which of these two compounds is more acidic? Oh, that's a much easier question to answer. The trick here is the context of the problem. So which one is the most acidic and which one is the least acidic? So we have HA, HB, and HD. Now, cool part about this problem is if we look at it, let's see what happens when we convert when we make each of these act like an acid. So if we make this one act like an acid, we get the carbanion. And if we remove HC, we get this compound. If we add HB, this is really hard to draw a 7-member ring. We get this carbanion. Now, you should start to see something with when we remove HA. You see a conjugated system. So in this case, and in this case, we end up forming a conjugated set of orbitals. Now, because they are conjugated, this means that we have the potential for resonance stability. That's not going to be true if we remove HC. If we remove HC, sorry for the glare, we end up forming this carbanion right next to a double bond, but there's nothing that can participate in resonance. So off the bat, HC is going to be the weakest acid, or HB is going to be the weakest. And it's going to be the weakest because there's no resonance stabilization. The question now is hydrogen A or hydrogen C, which one's the most acidic? So we've got a conjugated pi system. We have a ring. So the question is it aromatic? So if we use our 4n+2 rule, we have 2, 4, 6 electrons, we meet this. So this is actually an aromatic compound. There is a driving force to remove this hydrogen, so there's a good reason for this hydrogen removed. But if we do this one, or remove hydrogen C, we have 2, 4, 6, 8 electrons, which is not equal 4n+2. So in this case, this would be the most acidic, because if we remove that HA carbon, the HA hydrogen, we end up generating an aromatic ring, which is going to be more stable than if we have the hydrogen there. And this is something we see with compounds that are called cyclopentadienyl. So if we got rid of the methyl groups here, this is substituted CP, cyclopentadiene. It is actually really stable. We end up isolating it more in the ionic form than we do in the covalent form, and it's used as a common transition metal ligand. So it actually attaches to organometallic compounds because it's so electron rich. But this ends up being the most acidic because when you remove it, you end up creating a conjugated aromatic system. This one is the least acidic because there's no resonance stabilization. Now, This does not form an aromatic ring, but it can engage in resonance. And because it can engage in resonance and we can rearrange the structure, we're going to stabilize it. So while it's not as acidic as something like the HA hydrogen, it is acidic because there is a way to resonance stabilize that anion. And again, for HB, that's not going to be true. That lone pair is stuck next to that double bond, and there's nothing it can do about it. And the other question that I got asked was, I'm going to be honest, I don't know the answer to this question, so we're going to work it out together. We've got the reaction of this nitrile benzene ring. Oh, I know what this does. At least I think it does. Hold on. So, oh, I really hate it if that's what this is what your book actually did. And the reaction is potassium carbonate and H2O. Now, if I had to gander what's going on here, carbonate CO3 minus 2 is a base. So we end up forming hydroxide and bicarbonate. Well, we've got hydroxide and we've got chlorine here. We can undergo nucleophilic substitution. So we're not going to get attachment to the ring. This would be my guess. We're going to go check it really quick. You're not going to get attachment to the ring, but instead you're going to get either an SR1 or SN2 attack on this chlorine to displace it to give you the alcohol. So let's see if I'm right. Question 28. So let's show you some humility. Let me try it, because I don't actually know if this is the answer, but this would be my guess and my thought process. I think you're forming a base, and that base undergoes substitution of the chlorine. So this is my structure. Let's see if I'm right. Correct. Ha! I'm somewhat capable at organic chemistry. So to answer that question, what happens with the carbonate is that it's forming a base, and this base is going to undergo nucleophilic attack on the chlorine that's attached to the methyl group. So that's the purpose of carbonate, is just to form the base. Now, that's kind of an abstract way of doing it. Not gonna lie, I'm getting kind of used to organic textbooks doing that to me at the very end anyway. So, but that's the purpose of the carbonate, is to form a hydroxide, which subsequently attacks your chlorine. If it makes you feel better, I've been putting that problem off to try and figure it out in the back of my head. And it's just now hit me. It just hit me like a few minutes ago. That's probably what the answer is. All right, are there any other questions? That was a lot to take care of. I believe with both classes this week, you actually have your exams showing up this week. I know this is true for Organic 1. I haven't checked for Organic 2. But just a reminder concerning the exam, it is not due until Sunday at midnight, and this is by design. If you know you're not going to be available to take the exam this weekend, go ahead and get it out of the way. The homework is not due until Friday, I believe at midnight. This is to make sure that they're not due at the same time, but I also don't want you trying to do the homework and the exam at the same time. So by Friday, you're cut off with the homework. That should force you to do a little bit of studying before you take the exam. You're going to find, if you haven't read my Rate My Professor already, I prefer to make the exams easier than the homework. So if you're able to get through the homeworks, you should be sitting just fine for the homework or for the exam. You probably, like that mass spec problem we just worked, I would never give you anything that really hard on the exam. These are all multiple choice questions. You are held to a 75-minute time limit. This is for both Orgo 1 and Orgo 2. Again, this is also by design. 20 multiple choice questions. You're welcome, Nicole. 20 multiple choice questions. I don't like multiple choice. Makes them 5 points each. So if you get them wrong, get through them wrong, you're down a letter grade. But that said, they all weigh equally. So the easy questions count for just as much as the hard questions. So yeah, there's hard questions on there. You got 25% chance of getting it right by random guessing. It kind of works itself out in my opinion. But this is kind of what we're dealing with the pandemic. Ideally, what you would do in a seated class is we would take a real exam. But the 75-minute time limit is to keep you from trying to Google the answers. Particularly as we start getting towards like Friday and people start asking me questions. If they ask me a very oddly specific question, I might check during the live stream to make sure that's not an exam question. But again, feel free to ask me questions about content material. This weekend, probably not such a great time. Other big thing with the exam online. If you're taking the exam and you come across a problem and it is just weird, like it's asking something weird or it's just referencing things that we haven't covered, send me an email. I mean, take your exam as usual, but if you do say, hey, Professor Stewart, I was taking this test, this question was completely out of nowhere, and I look at it, if I conclude, and this is not like one of those fake promises, no, I'm being serious. If I look at it and I say, wow, we really did not cover this, or this is really completely out of left field, I'll give the whole class points back for that question because it is a question pool, and I don't think it's fair to hold you to things that we haven't really covered. Now, if it's just something where like it's presented in a different way, I'm less inclined to give you credit for that. But definitely, I've had it show up every now and then. And there's a few reagents I've actually added to my notes because of this. On the homeworks, they're completely out of left field. The textbook itself does not discuss it, it just kind of is. So on homeworks, I'm a bit more willing because we can talk about it to count questions that are completely out of left field. But on exams, definitely not. Big thing with the method section is getting rid of details that did not affect your answer. And the problem I get with method sections, because I definitely get a lot of students that try to like put down every little detail, is like, did the size of your flask actually affect your reaction? Or like, did the fact that, you use Excel really affect your answer? So in terms of repeated steps, it's fine to say like as was done before or beforehand. Typically for each part of a lab, it's usually 2 to 3 sentences for that particular method. Um, so you all did separation of a 3-component mixture for your lab report. And really you would just need 2 to 3 sentences for each particular separation. So for wash A, wash B, and the organic phase, 2 to 3 sentences each. Again, you don't need to state, so the volume you use is important because yes, if you use a bigger or smaller volume, it's your capacity to remove. But to say that you shook it 5 or 6 times, it doesn't really affect your answer. But that's how I would recommend keeping a method section short and concise. Ask yourself, if I got rid of this detail, does it affect how I do my discussion down the document? So if I say, I'll give examples of titrations because these are the easiest ones to discuss. Students will say, I used a 250 milliliter titration flask. Well, where did that 250 milliliters ever show up in your results and discussion? But to say that you used KHP and a sodium hydroxide solution, that's going to come up because you're talking about the reactions. To say that you use 3 grams of material, that's relevant because you're going to use the 3 grams when you start talking about your theoretical recoveries. But to say you used 125 ml separatory funnel versus the 250, you don't use that number anywhere in the calculations. So a true method section, if you were to write it for a journal paper, they would want a level of detail to make it sufficient for people to repeat your experiment. This is in contradiction to what I'm telling you, which is to keep it short and sweet. And the big reason I do this is twofold. One, it really teaches you to emphasize what's important. It helps you focus in on what were the relevant details in the experiment. The second is that, and I have had this, students will give me a 4-page method section. Not joking, 4-page method section for a lab that only had 2 parts because they're writing down every little detail, the make and model, the stir plate, things like that. And it's like none of that affected your answer. You're clearly just putting stuff down to pad your reports. So again, when you're writing your method section, if you're curious, if you want to know if what you've written is relevant, remove it and see if you needed it for your results and discussion. But if you can remove it and it never appears ever again in your lab report, it was probably an irrelevant detail. And these are not hard and fast. I mean, if you've got one sentence that's kind of superfluous, and I'm saying this to people who haven't had me before. If you have one sentence that's kind of superfluous, I'll write it in there, but I'm probably not going to deduct a point. If I do, it's going to be 1 or 2. But definitely if I get 2 to 3 page method sections, you're going to lose points because that is way too long for a method section. Like you're clearly just putting down everything for credit and not really thinking about the relevance of what you're doing. I would say for the separation lab, probably a half a page to a page will be about right. It did not accept number 6 as the most acidic. I seriously disagree with that. Okay, number 6. Oh, that's actually a mistake on my part. So when I wrote the diagram, it's giving you and I different problems. So let me go to your version of the problem on my end. I'm not going to be able to show it because it would show what your grade is. But let me take a look. Okay. So, Nicole, there is actually a mistake in your version of the problem. That's so weird. Because I knew I wasn't wrong. No way I was wrong about this. This is the figure it's giving you. This is the figure it's showing in the key. I knew this wasn't wrong. Sorry for how crudely drawn this is. So in the key for your problem, it shows another hydrogen. There's actually 4 hydrogens in the problem. But in the problem it's showing you, there's only 1 hydrogen in the first compound. So I can go back to my example because this is so weird. Cool. There's just no way that was wrong. Okay. So I'll share the desktop with you. This is what it's supposed to be showing you. Is that there's an HA up here, an HB, an HC, and an HD. So in your preview, which I just looked at, it doesn't have the HB. It has this as HA, and the top one doesn't exist. So in your case, the HB would be the most acidic. Now, HA and HD would not be acidic because of the well, they wouldn't be acidic because they both have lone pairs. But the other weird thing is that it would be a jockey between HA and HD as who's least acidic. So it's like they wrote this problem and then changed the problem halfway through because you're really just comparing HB and HC. You're not comparing HA and HD. So this is like a question that they half finished as far as I can tell. But that's why it's telling you that your answer isn't correct is because it's showing you the wrong figure. Oh, that's hilarious. So let me just go ahead and get rid of that question because that's hilarious. Oh, you were the answer we worked through is correct. The figure it's giving you is wrong, and the questions it's asking you doesn't make sense. Like, why would you have an HA and why would you have 4 hydrogens if you're only supposed to be picking between the two? So you were on the right path. It's just the version of the question it's showing you and the version that's even in the answer key, there are 2 different questions. Oh, that's hilarious. James, that's a good question. Like, I would have liked the version that you sent me. Because it forces you to think, like, okay, these 2 are definitely acidic, but one's aromatic, one's not, and then the other one doesn't have any resin state. Like, that's a very good problem. You should go steal it for an exam question. But what it has, like the actual key answer, is not a good question because you have 2 that would be poorly acidic, and there's a lot of hand waving as to which one would be the least acidic. And on top of that, it's not even makes sense because it's only picking between the 2 ones that are grayed out. So why would you even bother to have the other 2 hydrogens if you're not going to consider them? Yeah, I'm going to swipe that problem for an exam. That's a good question. Just not the way they did it. Yeah, when I looked at it, I was like, there's no way that's wrong. I looked at the keys, like, those are not the same figure. Cool. All right, other questions? I'm glad to hear it. Like, it, the original problem I thought it was a very good problem. I can see why they went down that line of reasoning. Just wish they had, like, finished there. Like, that's a great example of showing how resonance really affects, like, why aliphatic hydrogens are so acidic and why resonance makes them even more acidic. Like, that was such a great tie-in. All right, you're very welcome. Any questions out there? I've got, looks like 3 of you still watching, 4 of you still watching. All right, we'll go another 4 minutes. If I don't get any more questions, then we'll just head out about 5 minutes early. For those of you who are in organic too, it says the test one due date is September 11th. That's this Friday. I'm going to correct that. It's supposed to be September 14th. Don't freak out. I see that now. I think I misassigned it with the homework because the homework also doesn't appear to have a due date. All right, if there are no more questions, we'll go ahead and head out. Again, we've got a live stream tomorrow and we've got a live stream Friday, and then this weekend you're taking your first exam. So, good luck, and I will see y'all, some of y'all tomorrow.